Hi everyone, this is Sean Long presenting you the first lab of Physics 2211. And in this lab, the purpose of this experiment was to measure the motion of a real-life object under a constant velocity, then comparing that data to a computer-generated model. And this allows people to observe Newton's laws of physics in real life. And a result preview is that it will show the observed object can get very close to constant velocity for a certain amount of time, as the data will show. And some key concepts we're going to go over that we're going to use in this lab is Newton's first and second law, which the first law states that an object in motion will stay in motion unless acted upon by another force. And a key concept that's derived from this law is constant velocity, when net force is zero in all directions, and where there's no friction, an object with no net force and an initial velocity will continue to move in that direction for an infinite amount of time unless it's obstructed by another force. And the second law states that force is equal to mass times acceleration, or force is equal to the change in p, which is momentum, over change in time. But in this case, force is zero, so the change in momentum is zero. And the assumptions, drag, and other forces like friction are ignored. And we are only looking at the x-axis, so y-axis and other axis movement are also ignored. Here's a computer model of constant velocity. And this is the actual experiment with a soccer ball where the surrounding is the normal force, gravity, floor friction, and air resistance. The system, of course, is the soccer ball. And some relevant formula and code that's derived from Newton's second law is the velocity update formula shown here, and which can be translated into the code that will update the object's velocity as time moves. Same thing down here, position update formula, which is also derived from Newton's second law, and which will update the ball's position as time moves on. Now, some of the initial conditions, the main one being the ball's initial velocity, is calculated by a changing position in the x-axis over the change in time, which we get as negative 1.2866 meters per second in the x direction. And this is the code that loops the computer model, which states that as time is less than zero point 0.7 seconds, the net force during this entire time will be zero to make sure constant velocity is possible. Velocity and position will update during this time, and the object will be plotted. Now, a simple comparison between the two is, as you can see, the red points are computer model, the blue point are the observed tracker analysis, and both are very linear and very close, only slight deviation. And that deviation can be explained by the difference in the center of mass due to human error, as we are estimating where the center of mass is in tracker. And the total net force on the soccer ball isn't exactly zero, but we assume it is. And that tiny bit of net force on this acting on the soccer ball causes the deviation. And some observations that we made during this lab is that when no net force is acted upon an object, and initial velocity is present, the object will move in a constant motion for a certain amount of time. And as we observed, the ball's movement was moving very closely to the computer model as it began, but as time moves on, it deviated more. And here are some what ifs, and what does it mean? If we flip the axes, the graph will be reflected over the x axis, the slope will become positive, but magnitude and position will not change. Uh, and it's not possible for us to say how many pushes and pulls from the surrounding because there's just too many things to consider, like gravity and drag. However, since the ball is moving very close to constant velocity, the experiment concludes that net force is near zero. And we can conclude that with no net force during this time period, the observed velocity remains very close to constant, and the computer model successfully predicts that, and our object successfully proves Newton's second law.